Hello, in this session we focus on integration, especially the use of standard formulae during the exam. There are integrals that would be otherwise longer to solve if we don't use standard formulas. Where it is possible to use standard formulae in the exam, it is advisable to use them so as to move fast. Integrals where standard formulae are needed are those that have to do with partial fractions, or those that need a substitution, usually of the type that is trigonometric or hyperbolic function. In particular, we have the first case, the standard integral 1 all over a squared minus x squared dx, which is supposed to be 1 all over 2a ln of a plus x all over a minus x, plus the constant of integration. For you to use standard formulae, you would need to have arrived an integral which is similar to a particular standard formula. This case has to be where you have a rational function having a real constant at the numerator and difference of two squares at the denominator. The next thing is to make sure the coefficient of the square of the variable at the denominator is 1. When that happens, you now go to the standard formula, usually by first reading the a on the left hand side, which is always the square root of the real constant, the positive real constant that is at the denominator. An example, we have integral of 1 all over 9 minus x squared dx. Here a squared is 9, and so a should be 3. Then I apply the formula directly. I get 1 all over 2 into 3, which is the a, ln of a, which is 3 plus x, all over 3 minus x plus c. And so the answer is 1 over 6 ln of 3 plus x all over 3 minus x plus c. You can otherwise do this integral by first expressing 1 all over 9 minus x squared in partial fractions. Under applied mathematics, we get very often integrals where we have to apply this, especially in a situation where we are modeling problems using differential equations. You have, for instance, integral of 1 all over g plus kv, minus kv squared dv. At some point when you are modeling with differential equations, you can come across an integral that looks like this. For you to do this integral now using the standard formula, which is here, you first make sure the coefficient of v squared is unity, which is 1. And I will do that by simply factorizing k. So I will have to write 1 all over that k, which I'm factorizing, then integral of 1 all over, I divide every term at the denominator by k, which gives me g over k minus v squared dv. 1 over k dot. You can now see that the denominator is identical to the one of the standard integral on the left hand side. And my a in this case is the root of g over k. So I'll have to write 1 all over 2 according to the standard formula. Then a being the root of g all over k. And then ln of that a, which is the root of g all over k, plus v, the variable being v in this case, all over the root of g on k again minus v, plus the constant of integration. And at the end, I get 1 all over 2k, this k times 2, and then I invert this other expression and it gives me the root of k all over g, ln of root g all over k, plus v all over root g all over k minus v. Overall, I simply square whatever is outside here and send inside, but rather I will leave the 2 outside to simplify. I leave the 2 outside since there is k in this other expression. I would simplify by putting 1 all over 2, the root of. I now take this k, and to put it inside the root sign, I square it. So overall, I will get 1 all over root kg, the square root of 1 over kg, ln of the root of g over k plus v all over g over k root of that minus v plus c. Where there are limits of integration, you then substitute them to obtain your result. There are cases also that you could have integral of 1 all over 4x squared minus 9 dx. In this case, the difference of 2 squares is in such a way that the term in x squared is positive. So, but in the standard integral, that coefficient has to be negative. So I start by factorizing -1. So that will give me integral of 1 all over -1 into. I divide every term by -1, so I will get 9 minus 4x squared dx. And I can further factorize 4. So overall, I will be having 1 over -1 over 4 to factorize. Integral of 1 all over, I divide every term in the bracket by 4. So I get 9 over 4 minus x squared. Sorry, there is no square root. And I can now have -1 all over 4 dot 1 all over. When I come here now, I have 9 over 4 minus x squared, and comparing with the standard integral, I see that a squared corresponds to 9 over 4, so a should be the root of that, which is 3 over 2. So 2 into 3 over 2, ln of the square root of 9 over 4 again, which is giving me a, which is 3 over 2 plus x all over 3 over 2 minus x, plus my constant of integration. This gives -1 all over 2 cancels 2, and I have 12 ln of 3 plus 2x all over 3 minus 2x when you simplify this expression, plus c. Another important example, this would be 5 integral from 3 to 4 of 1 all over 2 squared, if you like, minus x squared, so that a becomes 2. And so we get 5.1 all over 2 into a, which is 2. And then ln of 2 plus x all over 2 minus x from 3 to 4. This gives 5 all over 4 ln of the substitution of 4 up gives 6 all over -2 minus 5 all over 4 ln of the substitution of the lower limit gives 5 all over -1. Overall, we get 5 all over 4 factorized because it is common into ln of 6 over -2 is -3, and the absolute gives 3 minus ln of 5 over negative 1 is negative 5, and the absolute gives 5. You can now use laws of logarithm to simplify the final answer, which gives ln of 3 divided by 5. As I earlier said, you could still use partial fractions here, but it will be a longer method. The next standard integral is integral of 1 all over a squared plus x squared dx. This one is simply the case where you have a real constant at the numerator and the sum of two squares at the denominator. This should be equal to 1 all over a tan inverse of x all over a plus c. Again, to apply this formula, you will need to make sure that there is a real constant at the numerator, and that you are dealing with sum of two squares at the denominator, in which the coefficient of the square of the variable at the denominator is positive 1. An example, we have integral from 0 to 2 of 1 all over 4 plus x squared dx. This should be 1 all over a being the square root of real constant again, like in the first case, which is 2 tan inverse of x all over that a, which is 2. And we're integrating from 0 to 2. This gives half tan inverse of 2 all over 2 minus half tan inverse of 0 over 2. And we have half into tan inverse of 1, which is 45, pi on 4, minus half tan inverse of 0, which is 0. So the result is pi all over 8. If there was a situation where you had to do integral of 1 all over 9x squared plus 25 dx, again, you see that there is sum of two squares at the denominator and that there is a real constant at the numerator. The first step we have to do now is to make sure the coefficient of x squared is unity. We factorize 9, and so we have 1 all over 9, integral of 1 all over, divide every term by 9 as you factorize it. So we get x squared plus 25 all over 9 dx. We now have it that our a is the square root of the real constant at the denominator, which is 25 over 9. And so the square root gives 5 all over 3. And I'll have 1 all over that square root of 25 over 9, which gives me 5 all over 3, tan inverse of x all over that a being 5 all over 3, plus the constant of integration. And this gives the inverse of 5 on 3 gives 3 on 5, tan inverse of 3x on 5 plus c. Again, as you model with differential equations, you could come across an integral which has 1 all over g plus kv squared dv to do. You would then have to apply the standard integral again, which says 1 over a tan inverse of x over a plus c. 1 all over, so we have integral of that. I factorize k. In this case, again, I have to factorize k to make sure the coefficient of v squared is unity. And that will give k into, I divide every term at the denominator by k as I factorize. That gives g over k plus v squared, then dv. This will now give 1 all over k dot 1 all over the root of g over k, which is a tan inverse of v. The variable this time is v, all over, according to the standard formula, we have the variable v replacing the x, so divided by the a, which is the root of g on k, plus the constant of integration. So we could simplify this to, I'll square again the k and send inside. So it gives 1 all over the root of, so if I have k squared g all over k, it gives simply gk tan inverse of half the root of k, on g, and then v plus c. So the final answer will be 1 all over the root of gk tan inverse of the root of k on g, v plus c. The standard formula can even be applied in the case of integrals where there is the inverse of a quadratic function to be integrated. So we could have integrals of this form: 1 all over x squared plus 2x plus 10 dx. This would be 1 all over, so I have to complete the square at the denominator. I make sure the coefficient of x squared is unity, which is already the case. Then there is x plus half the coefficient of 2x, which is 1, all squared, minus the square of this half coefficient, which is 1, and then plus the constant term. This is another way, or a shorter way, of completing the square directly. I go again. So to complete the square using this shortcut, you make sure the coefficient of x squared is unity, which is already the case here. Then x squared, I write x, the sign that follows I copy. Then the coefficient of the term in x, I divide it by 2, which gives 1. All squared minus the square of that number that is here, which is 1. I then bring the constant term, plus 10. Overall, I will then get integral of 1 all over x plus 1 all squared plus 9, negative 1 plus 10. And with this now, this expression x plus 1 can be a replacement for x in the formula 2 as I'm performing the integral. So take note of that. It's a very big shortcut. It's a strategic method of solving this type. Once you arrive here, you are supposed to do a substitution using tan theta. X plus 1 equals the square root of 9, which is 3, and then tan theta. But it will be longer, so when you arrive here, after completing the square, just go straight to this standard formula and apply, where the x is replaced by x plus 1. So the answer will be 1 all over the root of 9, which is supposed to be the a. So 1 over 3 tan inverse of expression that is squared there, which is x plus 1 all over 3 plus c directly, and it gives you the answer. If you did substitution, you would arrive that same answer. If you had to do substitution, then you would have to say let x plus 1 be equal to 3 tan theta. And when you differentiate the left-hand side with respect to x, you get 1 dx equals 3 sec squared theta d theta. So dx equals 3 sec squared theta d theta. From there now, my integral would be 1 all over, I have to replace x plus 1 by 3 tan theta. So 3 tan theta all squared plus 9. And then the dx will be replaced by 3 sec squared theta d theta. This is dx. It has to be replaced to, as you are changing the variable from x to theta. From here, we have integral of 1 all over 9 tan squared theta plus 9 dot 3 sec squared theta d theta. This will be equal to, this 3 would come out of the integral all over this 9 that has to be factorized. So 3 all over 9 integral of 1 all over tan squared theta plus 1 dot sec squared theta d theta. And this gives 3 over 9, which is 1 all over 9 integral of tan squared theta plus 1 is equal to sec squared theta. It's one of the Pythagorean identities. So this is sec squared theta, which will cancel this one, and we are just left with integral of d theta. This is supposed to be 1 all over 3, sorry. Integral of d theta, which is simply theta plus the constant of integration. And from up there, tan theta is supposed to be x plus 1 all over 3. So that theta will be tan inverse of that. So we can see that this will be 1/3 theta plus c, which is 1/3 tan inverse of x plus 1 all over 3. The same result that we obtained by using the standard formula directly. So know that the standard formula is useful in these cases. It saves time. The next standard formula is integral of 1 all over the root of a squared minus x squared dx, which is supposed to be sine inverse of x over a plus c. So in this case, there is a radical at the denominator, the square root of difference of two squares again, in which the x squared, the coefficient of x squared is -1. That is the situation where you have to use this standard integral. So we can have an example integral from 0 to 2 of 1 all over the root of 4 minus x squared dx. And this directly, my a is 2 because a squared is 4, so a is 2, so I write sine inverse of x all over 2 from 0 to 2, which gives sine inverse of 2 all over 2 as I substitute the upper limit minus sine inverse of 0 over 2. This gives sine inverse of 1, which is 90 pi on 2, in radians, minus sine inverse of 0, which is 0. So the answer is pi on 2. You could have integral of 1 all over the root of 9 minus 36 x squared, and I would have to factorize the 36 to make sure the coefficient of x squared is -1 or unity. The x, that will be equal to the square root or integral of 1 all over the square root of I factorize 36 and then divide every term by that 36. I get 9 all over 36 minus x squared dx. This would be integral of 1 all over the square root of 36 would be 6, so I can put it out as 6. Then now we have the square root of 9 all over 36 minus x squared dx. And in this case now, my a squared is 9 all over 36. I will be talking of sine inverse of x all over the root of 9 on 36 which is simply half, plus the constant of integration, which gives 1 all over 6 sine inverse of 2x plus c. Note that you could complete the square and come up with integral of 4 minus x plus 1 all squared dx. You will still apply the formula. That will be sine inverse of the expression that is squared there, which is x plus 1, all over the square root of 4, which gives the a, which is 2, plus the constant of integration. For the fourth standard integral, we have integral of 1 all over the root of x squared minus a squared. It's similar to this one, but this time it is the variable that has a positive coefficient and the real constant is negative. So this time we are supposed to use cos inverse of x over a plus the constant of integration. And once you use cos inverse, you are likely to be asked to express the answer in terms of natural logarithms. You will then have to use the logarithmic form of cos inverse of x, which is ln of x plus the root of x squared minus 1, where x has to be greater than or equal to 1. An example, we could have 1 all over the root of 9x squared minus 47 dx, which gives integral of 1 all over the root of, I factorize, sorry, this should be 49. I intended to put 49. So we factorize the 9 because the aim is to make sure the coefficient of x squared is unity. So 9 into, I divide every term by that 9, I get x squared minus 49 over 9 dx. This would then give integral of 1 all over 3. The square root of 9 has to go out as 1 over 3. Then 1 all over the root of x squared minus 7 over 3 all squared, which means our a in this case is 7 over 3. Therefore, and so we'll get now the integral being the integral being 1 all over 3 cos inverse of x all over 7 on 3 plus c, which could still be 1 all over 3 cos inverse of 3x all over 7 plus c. And if you are required to express the answer in logarithmic form, then you proceed to 1 all over 3 ln of, use this one replacing every x by 3x over 7. So I get 3x over 7 plus ln of the root of 3x over 7 all squared minus 1, which should be 1 all over 3 ln of 3x over 7. Sorry, this is not having ln, sorry. Plus, this gives 9x squared all over 49 minus 1, the root of that, which gives 1 all over 3 ln of 3x plus 7 plus the root of, we have 9x squared minus 49 all over 7, because when you find the LCM and then you find the square root of 49, it will be 7. And overall, you could have 1 all over 3 ln of 3x plus the root of 9x squared minus 49 all over 7 plus c. For standard formula number 5, we have integral of 1 all over the root of a squared plus x squared dx, which is supposed to be sin inverse of x all over a plus the constant of integration. With this case too, you need to be familiar with the logarithmic form of sin inverse of x, which is equals ln of x plus the root of x squared plus 1 for all real values of x. Examples. This is very common in further mathematics exams, so you have to take note of that. I have integral of 1 all over the root of 4x squared plus 9 dx, which should be equal to integral of 1 all over the root of, I factorize 4 because I need to make sure the coefficient of x squared is unity. So I have 4 into, I divide every term by 4, I get x squared plus 9 over 4. This gives, the square root of 4 would come out as half. Integral of 1 all over the root of 9 over 4 plus x squared dx. It now resembles the standard integral in which my a squared is 9 on 4. So a should be 3 on 2. That now gives half sin inverse of x all over a, which is 3 on 2, plus c, which gives half sin inverse of x of 2x all over 3 plus c. Again, you could have to apply that to solve questions in which you have to complete the square at the denominator. A very good example, a past exam question, is prove that integral from 0 to 1 of 1 all over the root of 4x squared plus 12x plus 10 dx equals 1 all over 2 ln of 5 plus the root of 26 all over 3 plus the root of 10. It's a past GCE question. So my first step will be to complete the square. So 4x squared plus 12x plus 10 equals 4 into, I start by factorizing the coefficient of x squared, because to complete the square, the coefficient of x squared has to be unity. I divide every term by what I've factorized, which is 4. I get x squared plus 3x plus 10 all over 4. And that gives 4 into, I now complete the square, x squared, I copy x, the sign that follows I copy. The coefficient of x I divided by 2, I get 3 over 2, all squared minus the square of this number, which is 9 over 4, and then plus 10 over 4. So in the end, I get 4 into x plus 3 over 2 all squared plus negative 9 over 4 plus 10 over 4 gives 1 all over 4. Integral from 0 to 1 of 1 all over the root of what we have completed. That's the square 4 into x plus 3 over 2 all squared plus 1 all over 4 dx. This equals integral from 0 to 1. I would find the square root of 4, which is 2, and send it out, so I get half 1 all over the root of x plus 3 over 2 all squared plus 1/4 squared is the same as 1/4 is the same as half squared. And so I can now apply the standard formula, which has integral of this. In that case, I will be talking of this being equal to half into change inverse of this expression squared, that is squared here, which is x plus 3 all over 2 divided by a, and a here is half. From 0 to 1. This should be half change inverse of the same as multiplying by 2. The 2 would expand the expression up to give 2x plus 3 from 0 to 1. This will be half change inverse of substituting the upper limit. I get 2 into 1 plus 3, which is 5, minus half change inverse of the substitution of the lower limit. 2 into 0 plus 3 gives 3, and this gives half into change inverse of 5 minus change inverse of 3. I can now use the logarithmic form, which was specified up, to have half into ln of 5 plus the root of 5 squared plus 1 for this one, minus ln of 3 plus the root of 3 squared plus 1 for this other one. This gives half ln of 5 plus the root of 5 squared 25 plus 1, which is 26, minus ln of 3 plus 3 squared being 9 plus 1 gives the root of 10. And then laws of logarithm, I have ln of this divided by this, so I have 5 plus the root of 26 all over 3 plus the root of 10, and that gives the integral as required. We're asked to prove that integral from 0 to 1 of all this equals half ln of 5 plus root 26 all over 3 plus root 10. So you can see the importance of using standard formulae in the exam. Okay, you can now test your knowledge on these ones here. Show that a integral from 0 to 4 of 1 all over the root of 9x squared plus 4 dx equals 1 all over 3 ln of 6 plus the root of 37. Integral from 0 to 1 of 1 all over the root of x squared plus 2x plus 2 dx equals ln of 2 plus root 5 all over 1 plus root 2.